Hello. Today we will continue our discussion of reflection of plane wave at the dielectric interface when the wave is incident at an oblique angle. So we had earlier considered two polarizations, perpendicular and parallel, and we also computed the reflection and transmission coefficients for these two polarizations by satisfying the boundary conditions at the interface. Now what we do is we will consider one of the polarizations, and in particular we will look at the reflection coefficient and ask a very specific question. Let us consider gamma parallel, which is eta 2 cos theta t minus eta 1 cos theta I upon eta 1 cos theta I plus eta 2 cos theta t. And we ask that specific question: when will magnitude of gamma parallel becomes equal to 1? So we are asking the question, what is the condition under which magnitude of gamma parallel will be equal to 1? So we write down this equation. Observe this one within the magnitude sign, this equation here. This quantity will be, magnitude of this will be equal to 1 if either this term or this term becomes purely imaginary. Theta I is real, eta 1 is real, eta 2 is real. Therefore, none of them can become imaginary. What if cosine theta t becomes imaginary? If cos theta t becomes imaginary, the magnitude of this will be equal to 1. That's very easy. Just convince yourself. Oh, that's easy. It is of the form a minus jb upon a plus jb. So, now let's express cos theta t in terms of sine square theta t and use Snell's law and express this in terms of beta 1, beta 2 and sine theta I. Now we want cos theta t to be imaginary. That means it should be of the form j times square root of beta 1 by beta 2 sine theta I whole square minus 1. So for this to be imaginary, for cos theta to be imaginary, this quantity here must be purely real. That means the term here beta 1 by beta 2 sine theta I whole square must be greater than or equal to 1. That is, this is the condition. If this condition is satisfied, then cos theta t is imaginary, and therefore gamma parallel magnitude will be equal to 1. So this can be rewritten as theta I therefore must be equal to or greater than sine inverse of square root of mu 2 epsilon 2 upon mu 1 epsilon 1. If we choose the case mu 2 by mu 1 equal to 1, our favorite, then theta I will you get a condition for theta I, which is it should be greater than or equal to sine inverse of square root of epsilon 2 upon epsilon 1. We derived an equation theta I, it must be greater than or equal to sine inverse of square root of epsilon 2 upon epsilon 1 for magnitude of gamma parallel to be equal to unity. This situation is known as total internal reflection. That means all the wave that is incident on the interface is getting reflected back. So we have an angle which is equal to sine inverse of square root of epsilon 2 by epsilon 1 called critical angle, and the beautiful part of this critical angle is if the angle of incidence is less than critical angle, we don't see total internal reflection. If the angle of incidence is greater than critical angle, we observe total internal reflection. That is part 1. Second one, for theta I or theta C to be real and when the total internal reflection will happen, epsilon 2 must be less than epsilon 1. Therefore, when the wave is incident from region 1 with a permittivity epsilon 1 higher than region 2, which is with a permittivity epsilon 2, then we observe total internal reflection if the angle of incidence is greater than theta c. So a wave must always travel from a denser medium and impinge on the interface with the rarer medium. Then if you choose the right incident angle, then we can observe critical angle, or sorry, observe total internal reflection. Now we ask the same question, what happens in the case of perpendicular polarization? The equation for reflection coefficient is given here, which is gamma perpendicular, and we have the Snell's law given by beta 1 sine theta I equal to beta 2 sine theta t, and we also, using the same argument, we can conclude that theta I equal to theta c critical angle, which is given by sine inverse of square root of epsilon 2 upon epsilon 1. You can easily derive this result. It turns out to be very straightforward. We have assumed that mu2 by mu1 is equal to 1 in this case. Now let's plug these things into this equation here. Beta 1 is square root of mu1 epsilon 1, omega is there, and sine theta I is square root of epsilon 2 upon epsilon 1, and beta 2 is omega times square root of mu2 epsilon 2. The two omegas will be cancelled off. I'm left with sine theta t. Now we ask the question, what is theta t when theta I is equal to theta c, that is sine theta I is equal to sine theta c. That what we get is sine theta t turns out to be equal to 1, or theta t will be 90 degrees. So if a wave is incident at critical angle, the transmitted wave will be making an angle of 90 degree with respect to the normal. That means it will go grazing along the interface. Now what will be the value of gamma perpendicular? Of course it will be equal to 1. That's very easy to show. Straight away it's obvious because cos 90 is 0. And what is tau perpendicular? Tau perpendicular will be equal to 2. It's not 0. That's very important. That means when total internal reflection happens, even though the entire wave is getting reflected back with a reflection coefficient of 1, something gets transmitted to the other side also. That is very interesting. So what we are going to be learning more about is what is getting transmitted and what is the nature of that signal on the other side. So for that, what we do is we will calculate the electric and magnetic fields for the transmitted wave. So ET perpendicular polarization is AY tau perpendicular E naught e to the power of minus j beta 2 x sine theta t plus z cosine theta t. Can you visualize this? Yes. Given this E, we can also have an H perpendicular. It's straight away. And we know for theta I is equal to theta C, theta t is 90 degrees. Let us substitute that. What we get is AY E naught e to the power of minus j beta 2 x. Yes. Can you describe this wave? It is Y polarized wave and it is a plane wave propagating in the positive x direction. Yes, it goes along the interface. Yes, yeah. And H perpendicular will be AZ cap 2E naught upon eta 2 e to the power of minus j beta 2x. Straight away you can get this result. Now what happens when theta I is greater than theta c? Once again we are assuming that mu2 by mu1 is equal to 1, and this is the Snell's law, beta 1 sine theta I is equal to beta 2 sine theta t. And let's substitute the values here. Sine theta t is beta 1 upon beta 2 sine theta I, and beta 1 upon beta 2 is square root of epsilon 1 by epsilon 2. Why is it? Mu 2 by mu 1 is equal to 1. Correct. Now, this is greater than root of epsilon 1 by epsilon 2 sine theta c. Why? Because theta I is greater than theta c. We have chosen that theta I. Okay. But sine theta c is square root of epsilon 2 by epsilon 1. We know this result. And we can therefore substitute here. And what we get is sine theta t turns out to be greater than 1. How are we getting this? This term is greater than this, and if you substitute sine theta c in this equation, this will turn out to be equal to 1. Therefore, sine theta t is greater than 1. Interesting. We have cos theta t, which is imaginary, and we have sine theta t greater than 1. Looks good, looks cool, isn't it? Yes. That is the beautiful characteristic of total internal reflection. Now calculate cos theta t now. That is square root of 1 minus sine square theta t, and therefore we know this result also from the equation here. Straight away substitute that. And what do we have here? These are the two results that we have seen earlier, and we will now find out what is the equation for the electric field in the region 2, the transmitted electric field. Substitute the values of cosine theta t and cosine theta t. Sine theta t is given by this, and cosine theta t is given by that. This is the equation for the electric field in the transmitted region, the region 2. And now the next step is interesting. Next step is we are going to take out take this beta 2 inside, and then if you observe here, we are going to give this quantity beta 1 sine theta I a name called beta E, and this quantity here beta 2 times this term here, we give a symbol called alpha E. So if I define beta E and alpha E, then E transmitted perpendicular takes the form of a plane wave, which is Y polarized, which is propagating in the x direction with a propagation constant beta E, and in the z direction it is attenuated with an attenuation constant of alpha E. As theta I increases, this quantity increases, therefore alpha E increases, and hence it attenuates more and more. So when theta I is equal to critical angle, it was propagating along the interface, but as theta I increases more and more, the attenuation in the z direction increases, and this wave will be clinging onto the surface, and hence it is called a surface wave, but it is propagating in the x direction. Right, let's continue with our discussion. This is what a beautiful equation we got, very compact, with equations for beta E and alpha E known to us, and we ask the question, can we compute the velocity of this? It is easy. Velocity is omega by beta E, and is substituted and divided by beta 2, divide both numerator and denominator by beta 2. Omega by beta 2 is called the phase velocity of the wave in the medium intrinsic velocity, and therefore we have this wave Vpe as Vp2 upon beta 1 by beta 2 sine theta I. Now we know something here. Remember this set of manipulations that we did in the last slide? We are exactly doing it, but what is very interesting is, instead of taking sine theta t, we will take beta 1 by beta 2 times sine theta I, which will turn out to be greater than 1 because this quantity is 1. If you substitute sine theta c here, we get this becomes unity. Therefore, we have beta 1 by beta 2 sine theta I is greater than 1. That is, the denominator is greater than 1. What is the meaning of that? Vp2 upon Vpe is greater than 1. Right? Vp2 upon Vpe greater than 1 implies Vpe is less than Vp2. Hence, it is called a slow surface wave, because the velocity of this wave is slower than that of the electromagnetic wave, which is propagating in that medium, which is Vp2. Let's look at some images. This shows the picture of a wave incident at some angle, and the interface is here, and some portion is getting transmitted. If you notice, it doesn't satisfy the boundary condition. You can see that there is some gap here. There is no continuity of electric field. So in order to handle this problem, what did we do? We assumed a reflected wave. Right. So once we have an incident wave and a reflected wave, and you can see that the boundary is matched here nicely, there is a field continuity. And the total electric field in this region consists of a traveling wave in the x direction and a standing wave in the z direction. How did I get E1? It is sum of E perpendicular I plus E perpendicular R. If I look at the movie, you can see that the wave is propagating in this direction. This is the x direction, which is a propagating wave with a velocity beta 1 sine theta I, and in the z direction, it is a standing wave. Of course, the transmitted wave will propagate at some angle. It's fine. Now, what happens when theta I is equal to theta c? And we see that transmitted wave is propagating in the x direction, which is this direction, and it is uniform plane wave. Therefore, in the z direction, there is no attenuation, and it is plane wavefront can be observed. The angle is slightly greater than that theta c, or if it is greater than theta c, if the angle is slightly greater than theta c, then we see that the attenuation has certain value. It is decaying as it progresses in the z, as it propagates in the z direction. If theta is increased, then this attenuation constant alpha e increases and the wave clings to the surface. This is the surface or the interface between the two media. If I turn on the movie, what we see is the wave is still propagating in the x direction as given by e to the power of minus j beta ex, but it attenuates in the z direction. This is the nature of the wave in the region 2. So when you observe total internal reflection, we must ensure that the medium 2 extends at least to the region beyond the interface, so that this wave will not see any other interface. By the time the transmitted wave sees the end of that medium, it should have been attenuated sufficiently. If it doesn't, then we will not see a total internal reflection the way we have depicted here. Now, let us look at parallel polarization. We go through a similar exercise here. We have an incident wave and there is a transmitted wave, and yes, there is no reflected wave. How did this happen? We have an incident wave, we have a transmitted wave, the boundary is matched, and there is no reflected wave. Yeah, you're right. This one is incident at Brewster angle. I have chosen the angle of incidence such that it is equal to Brewster angle, therefore I don't see any reflection. Yes. Now, in case we can now therefore think of both gamma parallel and tau parallel. This is parallel polarization, so I see Brewster angle. Reflection coefficient goes through a 0, which corresponds to Brewster angle. Then it increases and becomes equal to 1, corresponds to critical angle. Beyond this angle, the reflection coefficient remains 1. This is the situation when the wave is incident from a denser medium to a rarer medium. And how about the transmission coefficient? It goes on increasing and hits the value 2 times eta 2 upon eta 1, and then it will start decreasing, and as theta I increases beyond critical angle, one more factor comes in, that alpha E, remember, that factor keeps increasing and the attenuation will be very fast. This is theta I is equal to 6 degrees, and when theta I is equal to 66 degrees, you can see that the attenuation becomes very fast. It has attenuated off very quickly.